Hi. Well, it looks like this webinar has just got started. Recording is in progress. I'm so glad everybody could join us today. I'm excited to officially welcome you to Detecting Change with Satellite Imagery and Open Source Machine Learning, a webinar based on MakePath's recent blog series, Machine Learning for Change Detection, which is accessible through the MakePath blog on makepath.com/blog. In this project, we didn't just evaluate changes in land cover using machine learning. We predicted future urban development of over 6,750 square miles of satellite imagery. We can now tell in a few minutes where future urban development will occur. This can help you make better decisions about anything from site selection to picking a new home. I'm joined by co-host, panelist, and machine learning expert, Dr. Dylan Stewart, MakePath's senior machine learning engineer and technical lead for this change detection project. I'm also joined by MakePath co-founder and principal, Brendan Collins. Brendan, do you want to introduce yourself? Say hello.
Yeah, thanks, Madison. I'm really excited to get everybody together today and just wanted to go ahead and thank all of our participants and speakers from the panel. There's a lot of great knowledge in the room. I hope that folks are able to also connect after this and see where there's synergy between the participants in the areas of geospatial analytics and also machine learning. I also wanted to mention that we have a limited release beta product coming up that I'm pitching. So if you go to makepath.com/change, you can sign up for that limited release beta. But Madison, I'll let you continue here. And thanks so much, guys.
Yeah, thank you so much, Brendan. I'm really looking forward to that beta product release. Very exciting stuff. Speaking of experts, I'm really excited to introduce the rest of our panel today in order of appearance during this webinar. So also joining us on the panel is Matt Ballard, a technical marketing manager at Planet, Matt Hampel, chief data officer at Regrid, and Thompson Comer, senior system engineer at Nvidia. So I want to dive right in. If you gain one takeaway from today, I hope it's that predicting the future is possible. So without further delay, let's hear from Dr. Dylan Stewart about what inspired this project and what goes into machine learning for change detection.
Thanks, Madison. You should be able to see my screen now. Is that showing up for you all?
Yes.
Great. So I'm really excited to share some of the work that we've conducted with our partners, Planet for satellite imagery, Regrid for the Parcel Data, as well as Nvidia for GPU and scaling tools. So I want to start just by showing you our study area, which Madison mentioned covers a little over 6,750 square miles of the greater Austin area. So this study area covers around 9 different counties. And so I'm going to show you some figures from the blog posts that we have about this. And I encourage you to check out those blog posts and feel free to connect after this if there's anything that you'd like to talk about. So the raster you see here is a mosaic of Planet imagery from May 2017, and we're displaying that in gray. And the changes that were detected from our deep learning model are shown here in green. So these are just raw detections that we're plotting here. And I want to just talk about a few areas of Austin. Here in the center here, we have the Texas Capitol, and down south here we have Buda, and in the north we have Georgetown. So one of the interesting things we can see here is that there are changes that are being detected over a variety of different regions, not just within the main area of Austin, but also within different neighborhoods. And we'll also look at a couple of examples here in just a few minutes that kind of zoom in on those different changed areas, as well as some interesting changes that we saw around Lake Travis and within the Colorado River area. So let's zoom in on a couple of these time sliders. One of them that was really interesting was this Colorado River area that feeds into Lake Travis. So here, this grayscale image is a 2017 raster. The green are changes that we detected from our deep learning model. And one thing I want to zoom in here on is these couple of dots here. If you can see my cursor, these are known as sometimes island. So these islands appear during times of drought or low water levels. So in 2017, the water levels were fairly high, so we can't see those. But when we slide over, we can see that in 2022, these islands pop out because there's been a bit of a drought. And so some of these subtle changes that our model wasn't necessarily trained to find, we're able to see things like that. And so this kind of adds in on other areas we might be able to apply this model to. And so I'll just slide this over and show that we can also see how these water levels have dropped and docks have been added in here, as well as other regions of this coastal area where people have been adding more developments over time. So I want to zoom in on sort of the case we were really trying to study, which is looking at where neighborhoods have been developed. So this grayscale image here is a 2017 raster. The green, once again, shows areas where we detected changes. And so when I slide this over, you'll see the 2022 image. So we can see that this neighborhood has been built up over the past few years, as well as changes in the roads here. And so this case really shows kind of what we were looking for with this project of being able to detect changes in a real estate type of case. So when we combine both the satellite imagery, we do the change detection, we can also combine parcel data. So I want to show this image quickly here. So this is where we've looked at where parcels have split in the last 5 years. We look at where we found detected changes from the satellite imagery from our deep learning model, and we subtract those two layers to come up with this final layer, which shows where are new parcels popping up, but we haven't seen any development occur. So this is really the key of predicting future development within the Austin area. So all of these green spots here are different new parcels which have popped up, but we haven't seen any sort of changes detected yet in the satellite imagery. So I want to just take a moment here and dive into sort of the technical details of how we're able to combine these different layers together, because we're combining parcel data, satellite imagery, and deep learning. And this gives us that ability to predict future areas of development. So I'm looking here at our fourth blog. So this is our technical deep dive. I encourage you to check out this video on YouTube where we walk through a Jupyter notebook showcasing all of the code that we put together for this. And so within some of the details here, we take the data, we download it from the Planet API. We create mosaics. So from the Planet API, we get several different tiles that we combine together to get mosaics. We load that data. So this is where our YouTube video starts, if you want to kind of follow along this blog post in your own time in the YouTube video. So we're using a variety of different tools, Rasterio, Rio X-Ray, other tools to help load in the rasters. We drop the infrared band because the Planet data that we're using is 3-meter data that has RGB and a near infrared band. We scale that data because we want the model to be able to pick up on changes within the different time periods. So we do some standard scaling of taking that 8-bit imagery and subtracting the mean, dividing by the standard deviation. So now we have this combined data set where we have 2 time slices, 3 bands from the RGB, and we have our spatial dimensions. So we normalize that data because we want to be able to pass in normalized data to our deep learning model. So I just want to show you these are the actual raw mosaics here. So this is from 2017 and 2022 of our study area. So once we have that data normalized and prepared, we can go ahead and use some of these tools for scaling like Dask, CUDA, which helps out with GPU, to be able to run our code in parallel and speed up the processing significantly. So we wrote a couple of functions here. One of them is it utilizes Dask map blocks. So what map blocks does is it applies a function across different partitions of the data. And so what we can use that for is we can load really large data sets in parallel and call functions on that data to be executed in parallel. So this first function works on forward propagating each individual sample through the model. We have another function which is copy and predict chunked. So this actually takes all of the chunks, breaks them into small chips that can be fed on to our model. And each one of these chips it contains a sample from 2017. It contains the same area from 2022. And then what we get back from our model is a mask showing areas that either changed or didn't change. So we parallelize all this code using Dask, using Dask map blocks. And we can visualize those results. So some of this stuff in here from the 4th blog post, you'll see in the Jupyter Notebook of looking at a small area and computing that. And I want to show here, this is the Dask dashboard. So we were using an A100 Nvidia GPU, and using Dask CUDA, we're able to scale up our code to run on several individual GPUs. So that A100 has 4 GPUs. So each one of these workers here, these 4 different bars, is a single GPU that is loading the data, breaking up the data into chunks, passing that data through the model, and we're getting back the predicted masks. Just want to highlight another tool that's pretty cool to use for visualizing and doing some spot checking. So we use Panel to be able to zoom in on different areas of interest and look at the change mask and be able to highlight regions of the 2017 raster and the 2022 raster at the same time. And we did a little bit of work of classifying some changes. So being able to look at where did areas of the mask change, and then look at the 2017 raster and the 2022 raster from those areas and actually classify those areas as, is this an urban area? Is this a rural area, etc. And so I encourage you, if you have any questions, feel free to ask those in this session. But I just wanted to give a quick highlight over the details here and really excited for this discussion. So thank you, Madison.
Thank you so much, Dr. Dillon. Yes, feel free to ask any questions in Q&A, and then they will all be addressed at the end of the session. I can't wait to pick your brain more in Q&A. Up next, we have Matt Ballard, Technical Marketing Manager at Planet. He's going to talk more on the satellite imagery that Dr. Dillon was mentioning we used for the change detection project. Off to you, Matt.
Okay, perfect. Is my screen coming across?
Yep, loud and clear.
Perfect. Yeah, thank you, Madison, for that introduction and for the opportunity to present here on behalf of Planet. As was mentioned, Planet is the provider of the satellite imagery that was used in that analysis workflow that we just looked at. And I'm going to be talking to you today just a little bit about what it is that we collect with our satellites and how it's used in these types of workflows. First, a bit about Planet. Our mission at Planet is to image the whole world every day and to make change visible, accessible, and actionable. So we're using this daily imagery that we capture to detect changes in combination with our partners and with our customers. And in order to achieve this mission, we've built the largest constellation of Earth observation satellites and a powerful software platform that you can use to search for and visualize and analyze our satellite imagery. Our capabilities span things like monitoring, which is this daily global satellite imagery that was used for this analysis workflow. Tasking, which is high resolution on-demand imagery when and where you need it. With the imagery that we capture, we produce mosaics over broad areas, which we call base maps, that are used in analysis workflows because of their visual and scientifically accurate consistency across time. And as well, we offer a massive catalog of all of this historical archive data that we've captured. And the example that was shown, that imagery was from 2017, which is useful to use as a baseline. The imagery is always being captured. And so we have this archive that you can always go back and pull from. You don't have to worry about whether or not satellite imagery was purchased and captured back in 2017 or 2018 or whenever you're comparing to. It's just always there in an archive. Now, in order to deliver these capabilities and solutions that we offer, we have 2 constellations of satellites today. One is called our PlanetScope constellation, which is made up of approximately 200 small sats, which we call doves. These are approximately the size of a loaf of bread, and it's the one that you see on the left there on the slide. There are, as I mentioned, about 200 of those in orbit today. The second constellation that we have is our SkySats, and these are high resolution tasked satellites. So these are ones that are directed to capture as needed. For the analysis that was shown just now, the PlanetScope Dove satellites were used. So I'll talk a little bit more about what this actual data set is and what technical aspects are of this data set. So one, this data set is at 3.7 meter spatial resolution. So that's the size of the pixels as far as what they represent on Earth. So this is sufficient spatial resolution to pick up on things like urban development, like we saw in the demonstration there. This is high frequency, so these are daily global scans, meaning that you can compare imagery from often as recent as yesterday, depending on variables like weather and cloud coverage and more. But we're looking at imagery that's very frequently updated, which is useful in places like Austin or this corridor where development is occurring so quickly and so rapidly. It's global coverage, so you're always we're capturing it globally across Earth's landmass and coastal waters, meaning that you're able to go and study an area on demand as needed. And what was shown in the imagery examples earlier today was it is a true color, or we capture spectral bands that enable you to create true color visualizations, right? So that's a red, green, and blue color, which you can imagine makes a visualization as if you're flying over this area of interest. But in addition to those bands, we capture 5 additional spectral bands: the second green, yellow, coastal blue, red edge, and near infrared. And these are essentially characterizing different wavelengths of light that have stronger signatures for example, for vegetation. The near infrared band highlights areas where vegetation occurs and can be used to help make a more accurate model to characterize land cover, such as in this example here. So these extra spectral bands help to pull out and differentiate by adding this like extra dimension that you can use in your machine learning models. And I already talked about the archive that's available. As a quick highlight of how our platform works, we aggregate data through an automated data pipeline from both our proprietary sensors, PlanetScope and SkySat that I've been talking about, but also public data from Landsat and Sentinel-2. And we ingest all that information, process it, and make it available through this archive that I've described. That archive we use for mosaic and image processing algorithms that we provide, but also we provide a RESTful API that customers and partners can use to extract, find imagery over their areas of interest and over their times of interest, and bring that imagery into their applications, into their notebooks, into their scripts, processes, whatever it is that you're intending to use the imagery for. And as you saw today, that it can be used for detecting things like urban development, looking for structures. This is just a similar example using our monthly global base map over an area in Tanzania where we detected buildings and compared that against OpenStreetMap, so a public data set available for building footprints. You can see the updates that are available through detecting from imagery that aren't in these public data sets, for example. And so that's really the benefit of satellite imagery, is that, and especially with our imagery, is that it's recent, enables you to get the most up-to-date information of what it actually looks like in your study areas. That's everything I had. Thank you for this opportunity again, Madison, and I'll pass it over to the next presenter.
Yeah, thank you so much, Matt. I mean, it's so amazing to hear that the Dove satellites are only the size of a loaf of bread. I had no idea that they were that small. That's a whole lot of punch in a very small device.
Yes.
Yeah. So, well, I guess moving on, next we'll hear about the parcel data that we combine with Matt's satellite imagery at Planet to predict urban future development. So Matt Hampel, Chief Data Officer for Regrid, you're up.
Thank you very much, Madison, for that introduction. And thank you so much to the MakePath team for having me here and for this collaboration. So my name is Matt Hampel. I'm the Chief Data Officer here at Regrid. And let me know if my screen is not coming through well. But we've been, Regrid is a property data and mapping company based out of Detroit, Michigan. We operate nationally and we collect data on every property in the United States. And I'll talk a little bit more about what we do in a second and about the scale and scope of the problem and how we can use this data for tracking change. But first, a little bit of background about parcels. I think we all at this point might be sure that we're not talking about this kind of parcel. We're not talking about the kind that UPS will drop off at your front door, but we're really talking about this kind of parcel, land parcel, geographic description of the area of a piece of land. Often includes a lot of metadata around it about who owns it, where it is, and additional context. In the United States, we all live on a giant land grid. Most of the nation is divided up into rectangular sections measured by a chain starting in the 1700s. Some places the land divisions date back even further than that. So when you're talking about change, at least in the US, there's a long history of recorded change and of course a long and sordid history of changes and problems with land ownership and tenure in the United States. That is what we really care about here at Regrid, and it's where we come from as a company. So if we fast forward 200 years, that's the story of where we are today. Founded in Detroit, we got our start in the height of Detroit's foreclosure crisis, when along with the whole nation, a lot of municipalities and localities were struggling with fallout from the Great Recession and the impact on property. We really care deeply about that in Detroit, and that care has grown out nationally. But the importance is really national. A large amount of the US economy revolves around information and property. In the United States, about $500 million worth of tax revenue fuels our local government. And then beyond that, knowing who owns what and property ownership rights drive a lot of what we do. We've been interested in change detection from the start. Here's the simple version. This doesn't involve a graphics card. This involves dozens of surveyors hitting the streets of Detroit in the 2000s, collecting data on every one of the 300,000 properties in the city, a little closer resolution than the satellites, but needed for this project, start of a larger data collection project we've been involved in since then. Our data collection efforts have evolved from something local to something national. Today, we carry 154 million parcel boundaries, numbers growing by the week. It covers more than 99% of the United States population, and it's a really large data set that underlies so much of what the American economy is driven on. We have data on nearly every property in the nation. And what do people use this for? And what do we do here at Regrid? So our mission is really to get this data into your hands and make it usable for projects like this change detection. We make it browsable for free at regrid.com. We enhance it with an additional pro information tools, and it's available via our data store. We also make it available in bulk for analysis. So if you're working on a large analysis, whether it's just one county and city or all 154 million parcel polygons in the United States, we can get it in your hands in a way that makes it useful. So, we're really excited to be working with MakePath on this project. And of course, a lot of other folks around the nation use this data as a key part of their business and good works. And just to set the stage a little bit, in case you haven't worked with parcel data, I won't read out all the different use cases that there are for parcels, but I do want to highlight a few here. Key, of course, data, AI, and ML and modeling. There's a lot more behind that. And in addition to that, if you if you like the outdoors, if you do hunting, fishing, hiking, you might have encountered parcel data when you're looking for the right trails to go on to make sure you're on public land and not trespassing on private land. That's a very clear application. If you used Zillow or Redfin, applications like that use parcel data behind the scenes to show you where properties are on a map. And there's many, many more uses on top of that. So it's really something that touches a lot of pieces of the world. But of course, in getting into the hands of MakePath, folks like Matt, Dylan, and the team, it's a struggle. And that's our job, is to get it in a clean, usable way for you to use. And I think it's something people often come into with this is, hey, this is public data. This is produced by the government and it should be out there in public. And We agree, and that's a big part of our mission. But there's a reason. It's not just all on open and on open data portal. And there's a lot of value that we bring and add on top of that. So there's no standards for property data in the United States. There's no coordination. And there's very little cleaning that's done at the local level, because for the most part, this data is collected to charge taxes on property to property owners. So behind the scenes, that's what we do. There are about 3,200 municipalities in the country that we collect data from. We clean it, we standardize it into a standard schema, and we enhance it with really great additions. So let me talk a little bit about some of those. Effectively, each of the United States 3,200 jurisdictions is administered independently. And this satellite view, this parcel view that we've accumulated, it's one of the only ways of looking at this data in a whole picture without dealing with all of those 3,200 municipalities. We've experienced through that many, many different situations. And I think the key is to focus that this data is originally produced for administrative use, and now we're trying to stretch it into these additional uses. So here's some of the learnings we have at the national scale. Some places still haven't hit the digital era. We're working to digitize parcels in parts of the country where the digital data doesn't exist yet. It's still on paper maps, surveys from the 1960s. I was looking at a survey map from the 1960s just yesterday that we're going to be digitizing. The other challenge is the number of formats that it gets into. When you're working with something for analysis, I would say 90% of the work is going to be in getting the data in a format where you can do it, where you can use it the way you need to. We take away a lot of the effort. That's our mission. Here's an example of an actual piece of property data we came in here. It's not something you can really feed neatly into a model in a way that's going to give you a structured output that's repeatable and scalable across the nation. It's an absolute mess across the country, and that's our job to take care of it. In addition, there's a lot of enhancements that can be done on that. You can combine it. We worked with a great partner to get 183 million building footprints detected from aerial and satellite and LiDAR imagery. An additional pile of matched addresses, so going beyond the parcel level into exactly what addresses are on every parcel. And for the team, something that we really wanted to bring to this partnership is the fact that you can bring your own stack, any technology stack. We're here to deliver into that. And we've worked with Parquet formats, especially for analysis. We can provide the data in your very common, your CSVs, your GeoJSON, the ways you want to consume it. And we're happy to work with you. And that's why we've been happy to work with makepath to get this data to them in a format that makes it easy to use. So beyond that, on a broader level, I do want to say, I think another unique part of this data set is that it's polygon data. Points are great as a start, but when you're looking at areas and changes over areas, you really want to know spatially where those areas are. And the polygon data that comes from parcels is great for that. It joins really well to other data sets because you're not trying to mash together a set of disparate points that might or might not line up and align with each other into one data set. This makes it easy to feed it into your models, and we're happy to share our knowledge and experience and connect you to great folks like makepath to make that happen. And the partners are really the key for connecting the data in. makepath brings an expertise. I think everyone in this call is bringing a really fantastic expertise in their domain. And it's really with this combination of powers that we can produce really interesting results. Finally, I want to talk about a couple of things that are next on the parcel data pipeline, because you might think, okay, property data is set in the United States. It changes all the time. So we're always working to improve our coverage of the data, our completeness and currency. It's along with this change detection, it's important because there is always that change, and that's a fundamental part of it. Part of it is how does that end up reflecting back in the data? And that's where I think I see some interesting potentials for collaboration in the future. If we're seeing change that isn't being reflected in the data yet, is that a sign that it's time to look closer there? There's still an enormous amount of standardization. I think the documents coming out of this project are really great in terms of systematizing processes for working with this data. Those shared resources, that shared learning that lets us take one project and then build it into the next project. And of course, in addition to that, there's a lot of room for classification, especially based on imagery, improved tooling around the similar pieces, and makepath contributes to a lot of those projects. all tied around changing, detecting change over time. And that's something we really care about. We've been building a database of history of parcels as well. It's something that we're really passionate about into the future, understanding how the history can be unlocked in a way that works for a lot of these applications. So thank you very much. With that, Madison, I'll pass it back to you and the team, and excited to hear more about the NVIDIA portion.
Thank you so much, Matt. I mean, it always amazes me that you can get 99% coverage, especially with how difficult it is to get that kind of data, especially if there's no standard schema. Really, really cool stuff.
Thank you.
Yeah. So now, next up, we have Thompson Comer, a senior systems engineer at Nvidia. He's going to tell us a little bit about how we scaled up change detection. To you, Thompson.
Thanks, Madison. Let me see if I can get this screen share going. I believe that it should be fully operational about now.
Yep.
So first of all, thanks again, Madison, and thanks, Brendan, for inviting me to participate in this panel. My role here today is just to be a little bit of a NVIDIA emissary, because we have a team at NVIDIA that's making tools available for developers like makepath and for companies like Regrid to try to get acceleration, to get more work done more easily. And we've got really a mix of individuals across teams that have been collaborating with makepath for months at this point. And so that's my opportunity to participate, is just as kind of a regular makepath collaborator. In particular, the relationship that I have with makepath, that NVIDIA has at this level, is makepath comes to us with features that need to be developed, and we come to makepath with knowledge of how to use the tools that have already been built. So it's really a great relationship. It's exactly what we are looking for on the team that I'm a part of. So I'm Thompson Comer. I got a master's degree in artificial intelligence, machine learning, and computer vision back in 2009. It's a fun anecdote to share, because NumPy was in its infancy when I was a graduate student, and I got to play with like the beta version of NumPy, and I was kind of like, I'm not really into using Python for data science at the time. It was all R and S+ at the moment. I work at NVIDIA. Most of you know who NVIDIA is at this point, but NVIDIA's relationship with the consumer market is changing, and I want to communicate about that a little bit. I always present to people when they find out that I work at NVIDIA that, yeah, of course, we make video games graphics cards. And that's where NVIDIA really developed from a nascent company into a world power. But in recent time, what we're trying to do is accelerate scientific computing more than gaming computing. I mean, obviously, gaming cards are of super high importance, and they'll continue to be the bread and butter at NVIDIA. But it turns out this is something that was developing again during the time when I was a student and I was learning machine learning and data science, was that GPUs actually turn out to be fantastic for accelerating numeric computing, and that the big bottleneck with all of science in terms of computing in the time around when I graduated 2009 or so, the big bottleneck was that you can't get so much done if you have to do everything in sequence. If you have to do it in order, most of the hard computer science problems are NP complete. They are polynomial or exponential complexity. And if you want to try to solve them in a short period of time on a realistic data set, you're out of luck. And so what NVIDIA does now is we build data center accelerators that are based on the architecture of computer graphics, but provide you, the purchaser of a graphics card or of even a data center or of a server, a rack mount system, you get the opportunity to convert certain types of computing tasks that used to take 1 minute, 5 minutes, 10 hours, or 10 days, and accelerate that stuff using NVIDIA's hardware to take only seconds. So that's the team that I get to work on. I'm a member of a team called Rapids, and the NVIDIA team that is called Rapids is an almost completely open source group. The work that I do is all on GitHub. All of my collaboration is on GitHub. I do have a private NVIDIA Slack team that we are members of, but we also have a public Slack team called Nvidia-Go-AI that you can look up, and you can join the rest of the Rapids team. And if you have questions, if you have concerns, you hop on that link. And world professionals in GPU acceleration are basically standing by to answer your questions. Rapids is the name for the unit at NVIDIA that writes this open source software. And I'm in the tools business. Matt, Dylan, and Matt, you guys are gold miners. You're actually writing software using tools that are producing value that's changing the world today. And that's, a tremendous relationship for me to get to share with you. I'm working in the tools business. I make pickaxes. And so the Rapids model is NVIDIA sells hardware, we sell GPUs, but in order to sell them, we need to have software that runs on them that's easy to use, familiar, and really high performance. And that's what the Rapids team concentrates on. So there's a bunch of different subdivisions in Rapids that I want to talk about briefly. One of the lead subdivisions in Rapids, which I was a member of in my early years at NVIDIA, this October will be my 4th year at NVIDIA. And for the first 2 years or so, I worked on cuDF, it's called, which basically just stands for CUDA data frame. And it's a copy of Pandas. Okay, almost everybody in data science today, everybody involved in high performance computing is familiar with Pandas because we've got massive spreadsheets full of data that we have to do analytics on. We have to do extraction, transformation, and load in order to figure out what's actually contained in that data. And what cuDF is it's a library in Python that looks and acts exactly like Pandas that runs on a GPU instead of running on the host CPU and the host memory architecture. So cuDF has been designed. It doesn't work 100% of the time because of basic limitations in GPU architectural design. But cuDF has been designed to be a plug-and-place replacement for Pandas. And in about 95 or 99% of cases, you can take a notebook, you can take Python code that you've written that utilizes Pandas, and you can, at the beginning of your notebook where you import Pandas, you can say import cuDF as Pandas. You can bring in the cuDF Python library, pretend that it is Pandas, and 95 or 99% of the time it'll run out of the box, and you'll see massive performance increases that are really, really stimulating, actually, because it increases your productivity. It makes it easier to work. Now, there's many other Rapids libraries. cuML provides deep learning type, machine learning type algorithms like XGBoost and support vector machines. It's got many other methods for doing analytics. cuGraph is a graph analysis library. And then we've also got a developing suite of node and visualization libraries that are really important, such as Node Rapids and cuCrossFilter and integrations with various visualization libraries. Another one that's particularly interesting to me is QSim there. It's a computer vision and image manipulation library. So if you're getting involved in raster data, if you're doing spatial type work and you're looking for raster libraries that run on the GPU, help us make QSim more mature for the spatial space. And I bring that up because the area where I contribute most today is in QSpatial. That's how I developed this relationship with makepath. QSpatial is, it's pretty nascent. We've got a small team, and we're trying to figure out what the most important low-hanging fruits are in order to provide the best tools for the people who are asking for them. But the short to mid-term goal with QSpatial is that it's going to be a drop-in replacement for GeoPandas, just like cuDF is a drop-in replacement for Pandas is. So QSpatial has a library that reflects GeoPandas, and it runs on the GPU with really high performance compared to the tasks that you're used to doing on your CPU analytics. So that's the software team. It's open source. It's the place and the way that I collaborate with makepath. I want to talk about what NVIDIA does and what our hardware is for in a little more detail. So this is a very simple slide. And what it's presenting here is essentially two products. These are data center graphics cards. They're not graphics cards anymore, right? They're high performance computing cards. The A100 is our server rack mount style product that you can purchase. And you can purchase one A100, you can lease an A100. And then we also have customers that are purchasing dozens or hundreds or maybe even thousands of A100s that are all networked together at once. A single A100 has either 4 or 8 GPUs inside of it. And the GPUs that are in them, I think today, now this is not my team, and so I have to kind of make things up as I go a little bit. Exactly what's happening in our hardware space, exactly what products are developed and what their performances are, that's somebody else's wheelhouse. I have a desktop under my desk that has a GV100 GPU in it, which is the data center equivalent of the 3090. And that's typically about as much as I know about the hardware. Now the A6000 is the latest data center card. It's what goes into A100s. So A100s have 4 or 8 A6000s in them. You can put a single A6000 into a desktop computer. And they also make really cool PCI Express GPU expansion peripherals now. And you can take a laptop, plug in a USB 3 plug into it, and then put an A6000 next to your laptop in order to take advantage of these libraries. That's the important thing that has to be noted, is that if you want to use Rapids libraries, you've got to have a system with a GPU on it. It's got to have CUDA installed and be CUDA enabled. So the A6000 with 40 or 80 gigabytes of memory determines how much work you can do on a particular problem. Now, unfortunately, as you know, we're in a terabyte and a petabyte space where data is just growing and growing. It's unbelievably vast. And in order to take advantage of multiple GPUs at the same time, we in the Python space are mostly relying on the product called Dask, which was mentioned earlier by Dylan. Dask gives you the opportunity in Python to automatically parallelize previously unparallelized tasks. And we have a library for Dask called Dask QDF. And we're making progress now with Dask and QSpatial so that you can use spatial analytics across multiple GPUs. I have to point that out because if you don't have multiple GPUs, if you're not using Dask, you can typically only run one task on one GPU at a time. And what that means is that you have memory limitations. The main architectural benefit, well, there are two architectural benefits that I'll get into in a little bit more detail in a second. And stop me if I go on too long because I can talk for a long time, Madison. The main limitation that you have working on a GPU is the amount of RAM that you have. A GPU has many processors. They're all linked to super high performance RAM. And in a general architecture design, that is the way that your PC works, whenever you run out of memory, it does something called paging. It spills your memory onto your hard disk. And it's comically slow to spill your memory onto your hard disk, but everything on your host computer is comically slow compared to what we're providing for you at NVIDIA. So you don't even notice. Now, unfortunately, if we were to use a paging scheme on GPUs so that if you ran out of GPU memory and we spilled it to system memory, we're talking about orders of magnitude of deceleration in your performance. And so all the gains would go out the window. Talking about that means that if you have an 80 gigabyte GPU running in your system, you can trivially work on up to 40 gigs of data, and you're going to have essentially real-time execution on 40 gigs of data. Any configuration of 40 gigs of data working within the Rapids software library suite is going to have basically real-time execution. So if you're used to running an algorithm and it takes hours to run on a 2, 3, 5 gig data set, if you have a single A6000, you can turn 40 gigs of computation into seconds of wait time. All right, so the last slide that I have to present is just about what parallelization is, how we get GPU performance and why it's of interest to you. So a good example of this is in the spatial space. You want to run point and polygon. You want to do a spatial join. You want to figure out which polygons are adjacent to each other. If you're using GeoPandas running on your host, modern CPUs are very fast, but they can only do one job at a time. And so if you've got 100,000 polygons or 100 million polygons, you have to wait for your CPU to compare each polygon to each other polygon in sequence. And even if you're doing billions of operations per second, the amount of time that you can wait, as you know, as a developer, just becomes, well, it grows polynomially. Every time you add a few more polygons, your runtime goes up by a significant amount. How do we solve that problem with GPUs? Well, they're massive parallel processors. You probably already know this. So the A6000 that I was mentioning on the previous slide has 10,000 individual math processors inside of it. And so it's able to accelerate the work by doing 10,000 operations at a time. The baseline gain from doing that essentially is, when you're using the Rapids libraries, anywhere from a 5x performance acceleration, which is really pretty rare, through a 100x performance acceleration, which is really frequent, actually. Most of our algorithms run 100 times faster than the host implementation does. And then some of the algorithms have radically faster performance, such as point in polygon and QSpatial, compared to a naive iterating approach that uses GDAL and Shapely. Point in polygon using QSpatial is up to 10,000 or 20,000 times faster in comparing polygons and whether points are inside of them. That works because all that a GPU is a massive memory buffer that's connected with high performance interconnects to 10,000 CPUs at once. That's what this slide is for. That pretty much covers the material that I wanted to talk about and how NVIDIA can speed up spatial work. Come and check us out at the NVIDIA /geo-ai Slack channel if you have any questions. And then be sure to go to, I think it is rapids.ai, to get access to all the open source software suites. They're all on GitHub. You can talk to any of the developers, and it's all super important to us to make sure that we are developing the lowest hanging fruit, the tools that you need. So if you are working on an acceleration problem, if you have a GPU at your disposal and you're trying to figure out how to use software that's going to save you time and make you money, reach out to me. Thanks, Madison.
Thank you so
Let me
much,
turn this off.
Thompson. Yeah, thank you so much. That's fantastic. Like, if anyone has any more questions about, how they can use GPUs to scale up their own analysis or certain kinds of problems, this is the perfect time to ask it as we transition to the QA section of this webinar. We've heard from all our panelists, so I just want to open up the floor to questions. I see we have a few in Q&A right now, so I'll start with those and make sure that, if you have any more questions, you just add them as we go along, either in chat or in the QA section. But before I begin, Brendan, did you want to say anything before Q&A, or did you want to just be part of Q&A?
Outstanding stuff. One just follow on comment, Thompson, is, we're integrating with CuPy and QSpatial in X-ray spatial, which adds additional GIS functionality on top of the X-ray library. And one of, I think, the interesting things here is there's technologies that exist in the larger data science ecosystem that can be tailored for specific domains like GIS. And that's one thing that we're doing in X-ray spatial, is naming functions in ways that geospatial professionals recognize. So, we're really excited about QSpatial and also QSim. So I guess just as a call to action for everyone attending, going over to QSpatial and looking at some of the features and making suggestions on what additional features you'd like to see out of that library, because that's a really exciting one. So, but thanks, folks.
Thanks, Brandon.
Awesome. Thank you so much. Yeah, so let's see. Our first question in the Q&A is, what use cases have you applied change detection to, and what use cases are possible? This seems like a question for Dr. Dylan Stewart, but of course, if anyone else wants, any of the other panelists want to input as well, you're welcome to.
Sure, I'll take this one away, Madison. So far, the use cases we've applied the change detection to have been for tracking real estate, and also some of the time sliders that we showed in the blog are for other things like looking at drought. I think another interesting thing which kind of highlights an event kind of going on right now in the Southeast is we could apply these change detection models to things like looking at, natural disaster damage, right? Of assessing an area before and after a natural disaster, which is a huge use case. But I really think about things that temporally short amount of time, like a natural disaster, or even a longer amount of time of maybe there's a huge construction project that we want to be able to track and check in on every few months or something. So yeah, there are a lot of different use cases where we could think about, where do we want to analyze change? Where do we want to track change? We've applied it to a few cases, but I think that's another interesting thing of this beta that we're launching in the next few months, is having more and more niche problems that we're going to apply this to.
Great.
Hey,
Well, I
Brendan,
know.
Oh, sorry,
Go
Madison.
ahead, Thompson.
Oh, I wanted to follow up and comment on another really important use case of change detection that I think is going to be relevant in the near future, and that's detecting environmental changes, right? We know that the environment is changing, and one way that we can actually understand where those changes are taking place is using a model like what Dr. Dillon has built up. I think that being able to predict where changes is going to take place is also going to be super gainful in the long term for trying to deal with the consequences of environmental change.
Yeah, that's really insightful. I feel the same way that environmental changes are going to be a huge part of the future of change detection. Looks like we have, speaking of different models, we have a question about hardware limitations. So Jorge Sepulveda asks that, have you encountered any hardware limitations with your models, and what were they like with the current graphics cards you have on hand?
So there weren't any limitations. We were using an A100 with 40 gigs of RAM. So there haven't been any limitations. The model that we're using is around 50 megabytes. So I can imagine we scale it up to even larger areas. There might be some limitations of where we get in touch with Thompson and rent out hundreds of GPUs if we need that, if we wanted to do some kind of extremely large scale area. But for around 7,000 square miles that we're looking at, we were able to do that with just using an A100 with 40 gigs and didn't really run into any limitations with that.
Great. Well, that's great to hear that there's no limitations. That's always great for when you're trying to scale up projects. So speaking of scaling up projects, what do you think is the best first step to scale up geospatial analysis? So would that be exploring like machine learning as an option, different libraries, or would purchasing a GPU basically be the first step you should do if you're dealing with lots and lots of data?
Brendan, do you want to take this one away?
I think that that GPUs are now available on several different platforms, including GCP. And it's really nice to be able to get an instance on GCP that's pre-configured with all the CUDA drivers so that you can get to just working on your problem as opposed to the DevOps side of some of this. And from there, where you see need, you can make other arrangements for getting hardware. But getting the hardware, I don't think is too difficult now with all the different options that we have to rent it, including Thompson mentioning leasing. But I think in terms of getting going and scaling, a lot of the solutions that we looked at here with Dask is a great takeaway here for horizontal scaling, where you want to scale out to many machines or maybe even just many cores on one machine. But then also the vertical scaling. So what the GPU in making all the algorithms much faster, like point and polygon, as Thompson mentioned. But then also tools like Numba. So Numba is a great library that pairs well with Dask that accelerates your Python code using a simple syntax for just-in-time compiling your Python code. So what we do is we combine Numba and Dask together, and then we have a decent solution that keeps us within the single programming context of Python, but allows us to target modern hardware like CUDA-enabled GPUs while not having to context switch to say C or C++, or writing a C extension in Python. So I think in terms of just getting going and scaling, choosing a project that you're passionate about, that you're willing to put time into, that you just can't put down and you can't stop thinking about, that's really helpful to get you over some of those initial technical hurdles that require patience. So when you have a great project that gets you going, that's really helpful. And then would also just would urge people to get involved in open source projects. Even if you don't have too much experience in coding, there's a lot of work to be done in terms of documentation, testing, helping with roadmaps and feature requests. So there's a lot that people can do without necessarily going in and writing code if that's not your technical level at the time. Also, great way to learn and improve your coding ability is by reading the code from other people in open source libraries. So my OS pitch.
I want to follow up on you again, Brendan, because that subject is particularly dear to my heart. If you're trying to learn to become a developer, if you want to get into data science or deep learning or machine learning, the world is really your oyster right now, and you can take that opportunity. You know, the best courses in the world are free. Almost all of them are available for you from MIT or from Stanford. You can watch YouTube videos by 3 Blue 1 Black. You can learn about technical subjects that you had to go to grad school for in the past. You can get a better education in that material today for free on the internet than you ever could before. And nothing is stopping you. So if you're motivated and determined, go out there and learn the equipment, learn the software, and you'll be working with us soon.
And I'll add my own little tidbit here to that is for getting started in machine learning, like Thompson mentioned, these resources are free. And one that I would really recommend is a course like Fast AI that Jeremy Howard's put together with a group of folks, and just so many tools on how to do deep learning, and even just starting from what is machine learning, what is deep learning, and the concepts, but also with great tutorials and notebooks, and all of it open sourced and available. So I'll add that link in the chat as well.
Awesome. I love to hear all of this pro open source talk and all these resources. That's one thing I really do love about the open source community is everybody wants everybody else to understand what they're doing and to join them in contributing to projects. Speaking of machine learning and open source, it looks like we have a question about the project if it was attempted without machine learning. So basically, could a change detection project of this scale work without machine learning? Or I guess if it didn't work, you know, do you have more limitations when you take out the machine learning element?
So I'll just add in a little bit of context here of change detection has been a subject that's been looked at for decades now, and well before the advances of Nvidia GPUs and being able to scale up deep learning solutions, you know, in the past 10 years or so, people were doing things with traditional analytics and detecting changes with statistical techniques that weren't using any kind of data-driven models. I will say, though, that the time that it takes to do those things can be significantly longer. The nice thing about having modern hardware and techniques that have been developed over the past few years with accelerating deep learning is that we're able to really scale up change detection across large spatial areas very quickly. So it's still possible to do it, what I would say, you know, the traditional way of using techniques that were developed decades ago, but it would be limited in how long it would take to do the processing.
Yeah, thank you. Thank you for that. It looks like we're starting to run up on time here, so we'll just answer one more question. And then if anyone has any extra questions, they could email me at madison@makepath.com or contact@makepath.com. So this last question here looks like it's directed towards Matt Ballard about planet data. So what is the smallest thing we can see in planet satellite imagery?
Yeah, the smallest discernible feature is dependent on the spatial resolution. And I mentioned in my slides, there's two satellites that we have. One is about a 3.7 meter spatial resolution satellite constellation, and the other one is about a 70 centimeter. And that doesn't mean per se that that's the size object that you can see. It's typically going to be like 2x the spatial resolution. I believe we could talk about it in more detail if you'd like, but think about that as the size of a pixel within the image. So if I'm trying to see something, it needs to be probably more than 1 pixel. So it's going to be maybe like 2 pixels by 2 pixels, and that could be like a car, for example. That's you know, a number of meters by number of meters. So it really depends. It's somewhat variable, but hopefully that gives you some context for what you'd be able to discern.
Awesome. That gave me some context for sure. So, well, I'd like to thank the panelists for their participation in this webinar. Now that we're reaching the end, I just want to pass it over to Brendan Collins to say a few words. Brendan?
Yeah, so for anyone that joined late, I just wanted to mention one more time that we have a private release beta coming up. You can sign up for that at makepath.com/change. Just wanted to thank again all the panelists, and Madsen, thank you, and thank you to everybody that has come to spend some time with us, and I hope we all get to connect again soon.
Awesome. Well, thank you so much. Thank you everyone for joining us. Remember, if you go to makepath.com, you can contact us for more questions through our contact sheet. And then if you email me directly, I'll put my email in chat right now. I can help you get connected to the right people to answer your questions and inquiries. Awesome.
Thanks, everyone.
Thank you very much.
Thank you all.
Thank you.